All right. Hello, class. This is going to be a super short lesson, or a fairly short lesson. And basically what we're going to talk about today is wind turbines. Okay. All right. So wind turbines. So we've got what does a wind turbine look like? It has a giant tower. There's and then there's a propeller at the top. The propeller is going to be spinning the loop of wire in a magnetic field, which will generate electricity. Okay. So basically when the wind blows, it hits the turbine and it spins the turbine blades around, and we get electrical energy. So I would like to get a formula for the power that a wind turbine can extract from the wind. Okay. And so the basis for this equation for power is going to be force. Work, or we didn't derive an equation, I just defined work. Work is force times displacement. If we take that and we divide by time, on the left-hand side, we have work per time, which is power. And on the right-hand side, we have force times velocity, because displacement over time is velocity. So power equals force times velocity, where of the fluid. Okay. And F is the force exerted by the fluid. Okay. All right. So what is the force exerted by a fluid? Well, that comes from the theory of fluid dynamics. And it turns out that the force exerted by a fluid is going to be 1/2 rho v squared times A. So what are all of these quantities? Rho is the density of the fluid. V is the speed of the fluid. And A is the cross-sectional area of the fluid flow. Okay. And so when I say that, what I mean essentially is if you think about all the wind, it's the area of the area that is swept out by the wind turbine. So if we think about this as basically like a tube of air that's being fed into the wind turbine, it's the area of that tube. So it's just going to be pi r squared, where r is the. So that's the force. So I can take that and I can plug it in for force. And so you can see that we have v squared times v, which is v cubed. So we can write that as 1/2 rho a v cubed. And of course, all energy production processes, none of them are 100% efficient. So we take this and we multiply it by the efficiency of the energy production process. And this is our equation for the power from a wind turbine. Okay. Now, wind turbines are actually not very efficient in some cases because if you think about it, these blades, there's gaps between the blades, and wind gets through the gaps between the blades, which means that that kinetic energy was not harvested. So that's something to think about. So you might say, well, why don't you just make the wind turbine blades wider, for example, so that they're being hit by more of the air? Well, if that happens, then the wind turbine might be so large that it just stops the flow of air. So you kind of have to be careful. There's a balancing act there. You want to capture as much wind as possible, but you don't want to stop the wind. This equation works for wind turbines, and it works for hydroelectric generators, because a hydroelectric generator still has a turbine that's spinning. The only difference is the thing that is the fluid that is making the thing spin is water, not air. So there are two densities you should know depending on what is spinning the turbine, okay? If it's water spinning the turbine, the density of water is 1,000 kilograms per cubic meter. If the thing spinning the wind turbine is air, then the density is 1.2 kilograms per cubic meter. So what you can see is that because water is so much denser than air, it generates a lot more power for a given speed. So if you have a hydroelectric dam, it doesn't have to go as fast. Water doesn't have to go as fast to generate a lot of power, okay? Air has to go faster. The other thing I want you guys to notice is that there's this factor of V cubed. So that means that the power output varies extremely strongly with the speed of the fluid, all right? So for example, what if the speed was 1? Well, 1 cubed is just 1. But what if the wind speed were to double, so that the wind speed goes from 1 to 2? Then your power output is going to be 2 cubed now, which is 8. All right? What if you tripled the wind speed? It's going to be 3 cubed, which is 27. So basically the lesson here is that a slight increase in wind speed results in a huge increase in the amount of power generated. So what that means is if you place your wind turbine in the right spot, it makes a really, really big difference because it very sensitively depends on speed. Okay. So your daily item for today is simply to do a calculation, calculate the power output of a wind turbine or something like that. When we come back from winter vacation, or not winter vacation, what am I talking about? From spring break, we will be discussing climate change, and we're almost done with the course content. So after that, we will start to learn some other stuff. We'll talk about the final exam, etc. So that's all I have for today. I hope you and your families are doing well. It's too bad you didn't win the meme review, but better luck next time. And I hope you guys all have a relaxing spring break. Bye now.